Hello and welcome back to the third video in the I2C video series. We're going to go over the byte format. We know that every byte is 8 bits long, and this is true for I2C. It says every byte on the data line must be 8 bits long. The number of bytes that can be transmitted per transfer is unrestricted, and each byte must be followed by an acknowledgement bit that comes from the slave. We know from here we can see that data is transferred with the most significant bit first, right? So pretend that our first byte can be represented here in hex as hex 11. We know in binary that this is 0001, 0001, right? So if this is transferred on the data line, we're going to see 0001, 0001, right? With the most significant bit first. Another thing, if a target cannot receive or transmit another complete byte of data until it has performed some other function. So for example, if it's servicing an internal interrupt, it can hold the clock line SCL low to force the controller into a wait state, right here. So we can see here that line's held low until this internal interrupt is done being serviced, and then it's currently in a wait state, and then once it's released, everything can continue. The next thing is data transfer then continues with the target when the target is ready for another byte of data and releases the clock line SCL. Hello everybody, the next thing we're going to take a look at is acknowledge and not acknowledge, which we just consider ACK and NACK. The acknowledge takes place after every byte, and the acknowledge bit basically allows the receiver to signal the transmitter that the byte was successfully received and that another may be sent, right? So the simplest example that you can compare this to is looking at when you send a text message, right? You send a text message to someone, they receive it, and it shows up on your end as delivered, right? So that's kind of the acknowledgement that you get back that, hey, at least they received the message that I sent, right? From here, we can see that the controller still generates all the clock pulses, including the acknowledge from the 9th clock pulse. The acknowledge signal is defined as follows. The transmitter releases the data line during the acknowledge clock pulse so that the receiver can pull the data line low and it will remain stable low during the high period of the clock pulse. Of course, setup and hold times, which we're going to learn about later, must be taken into account. When the data line remains high during the 9th clock cycle, this is defined as not acknowledged signal, or NACK, right? So if the acknowledge is high, this is considered a NACK. If the acknowledge is low, that's considered, or if the acknowledge is 0, it's considered a low. The controller can then generate either a stop condition to abort the transfer or a repeated start condition to start a new transfer. Now from here we can see there are 5 conditions that lead to the generation of a NACK. 1. No receiver is present on the bus with the transmitted address, so there is no device to respond with an acknowledge. 2. The receiver is unable to receive or transmit because it is performing some real-time function and it is not ready to start communication with the controller. 3. During the transfer, the receiver gets data or commands that it does not understand. 4. During the transfer, the receiver cannot receive any more data bytes. And 5. A controller receiver must signal the end of the transfer to the target transmitter. Another important thing to reference in this document is Table 11, which is the characteristics of the data and the clock line for all the different modes of I2C. This is really important because this is the characteristics that the standard specifies for the bus, right? So we have it for the clock frequency, we have it for the rise time, for the data in the clock line, for the fall time, the data hold time, the low period of the clock, the high period of the clock. A lot of these are very important characteristics, and you should reference this if you have issues with your I2C bus. As a final note, I would recommend looking at Section 7, which highlights the electrical connections of the I2C bus devices to the bus lines. One of the important sections that's included here is the pull-up resistor sizing, and it shows a lot of specific information, how the max possible pull-up resistance, how they calculated, what the formula is, different tables to look at, and it's really useful.